We are going to continue our discussion on using decarboxylation in biology, finishing up talking about how PLP can mediate decarboxylation. So the idea here is that histidine, the amino acid, can engage in imine formation with the PLP aldehyde. I'm not showing you that mechanism. You've seen imine formation before. And last time as we were finishing, I was pointing out how the resulting imine, this is the histidine portion, this is the PLP portion, this is the imine, is unique because it converts the alpha carbon of histidine into a place that can hold electrons. And I asserted at the end of class that what's in green here is now a good leaving group. And to illustrate that, I'll simply show you the decarboxylation mechanism. Electrons on the negatively charged oxygen kick down to make a new carbon-oxygen pi bond, and the leaving group gets kicked off, with electrons going on to the alpha carbon. So our two products of decarboxylation are CO2. There's the carbonyl carbon of CO2, there's the oxygen. And then what's left over here is the leaving group, which I'll draw real quickly. Here is the purple alpha carbon that's going to have the negatively charged, the negative charge, lone pair electrons on it. There's the nitrogen. Here's the double bond with PLP. And then we'll draw the rest of the PLP molecule, the 6-membered ring containing nitrogen, with the methyl group here, a positive formal charge on the nitrogen, and a phosphate group here. And this is the leaving group. Now, how is it that it can be a good leaving group? The answer is the negative charge is stabilized by resonance. So I could draw a resonance structure, exactly the same molecule, but it would look like this. And to get from the resonance structure on top to the resonance structure I'm currently drawing, you would simply need to push electrons. And I can show you those arrows. You'd simply do all of that. Okay, easy enough, right? What that shows you is that this negative charge on the alpha carbon is actually delocalized in all of those places that I've highlighted in pink, meaning that this is a resonance stabilized molecule, and in fact it's neutral. Look at this resonance structure that is no longer charge separated. It's totally neutral, I guess, except for the phosphate group. Yeah, okay, fine. Aspiring neutral molecule. Right, so that's why that can be a good leaving group. Now, at that stage, I'm going to erase those arrows to interconvert the resonance structures. If we now pick up a proton from the solvent or from the enzyme, I'm not sure what, so I'm just going to be generic. That will generate an intermediate, which is just the conjugate acid of what we've just drawn. So I'm going to save us a bit of time because we've got more important things to talk about today by erasing all the pink circles and putting hydrogen on that alpha carbon. There was already one there that's implied but not shown. In any case, and it's still an imine, sorry about that. Okay, and then all we do to get to histidine is we hydrolyze the imine, and then this portion here, oops, didn't mean to scribble it out, this portion of the molecule here is now histidine, or histamine, okay? So that's using PLP to temporarily make the alpha carbon into a place where electrons can go so that you can do the decarboxylation reaction. All right, questions about that? Yes? Yes, I was. Yay, I was going to be depressing. 5 minutes of test important content that was not going to be in the video. What's really depressing is when I go through a whole lecture or record an exam review video and I forgot to capture the audio. Then I usually just redraw it again. I don't attempt to narrate myself while I'm drawing silently. Okay, the last thing we need to do in chapter 17. Oh yeah, go ahead.
Are we responsible for this mechanism in the test?
You are now. Sorry. Are we responsible for this mechanism on the test? Sure, in the sense that it is simply an illustration of decarboxylation. It's not your fault. Don't blame yourself. Certainly, you would not be reproducing, say, the structure of PLP from scratch, but the mechanistic principles are very important. Yes. Okay. So, on the other hand, yeah.
I was just looking at your hydrolysis stuff from the amine to histidine.
Yeah.
Is that the same amount of carbons?
Is it the same amount of carbons? Yes. Everything here is abbreviated as R here. So nitrogen, alpha carbon, and then this is the R group.
Okay.
Yep. Others? Right. So there was a whole section of chapter 17 that's pretty straightforward to get, so we didn't spend a lot of time on it. This is called alpha-halogenation of carbonyls. There's a lot that we could do here, but we're only going to do a little bit. The idea here is if you take a ketone and under acidic conditions, usually this is acetic acid. This is both an acid and a solvent for some reactions. So you need acid to make the reaction go, and it's a convenient solvent. You also use Br2, and the impact or the effect of this is to put Br group on the alpha carbon. And the way this works is first you form the enol. So we've done that before, and so I'm not going to redraw that mechanism. This is ketone enol tautomerization. It's a great word. So here is the enol. And here's the alpha carbon of the enol. One important feature of the enol is that it has the following resonance structure that looks like this, in which there is a negative charge on the alpha carbon and a positive charge on the carbonyl oxygen. You should be able to convince yourself that those are two resonance structures of the same molecule. And so enols are nucleophilic on the alpha carbon. And so what happens next is that when you introduce Br2, the alpha carbon, the negative charge on the alpha carbon attacks the Br sigma star, breaking the carbon, the bromine-bromine bond, and that generates this oxonium ion intermediate in which we have one Br group on the alpha carbon, and then we'll regenerate well, we're not regenerating because we haven't even used an acid catalyst. Then some base, and it's either the conjugate base of our acid or it's Br minus. We don't really care what it is. I'm just going to abbreviate it. Your text probably shows you what it is, but we don't care. We're going to remove the proton from the carbonyl oxygen to get the product. Okay? So that is a convenient way of replacing a CH bond on an alpha carbon with a very useful leaving group. We call it alpha-halogenation because you're installing a halogen on the alpha carbon. Can you do this with chlorine or iodide? Yes. There are other variations of this reaction under basic conditions, other stuff we could talk about, but we won't. There are, however, we do want to spend a few minutes talking about things you can do with the resulting what we will call alpha-halocarbonyl compounds. Before we do that, any questions about that reaction or the mechanism? Sure.
Would it have to be a weak base in that example to not permeate the alpha?
Would it have to be a weak base here so as to not remove an alpha proton? Yeah.
Is there any limit that we need to know?
Is there any limit you need to know for practical purposes? No. Your text will probably show Br minus doing the deprotonating. Others? Yeah.
If we had an unsymmetrical ketone, is one alpha carbon more selective?
Right. For unsymmetrical ketones, is one alpha carbon more selective than the other? Because this involves ketone enol tautomerization, if I'm guessing, I would say you form the more stable enol and it reacts from there. In practice, none of the problems, I think, are that complicated on this subject. So, yeah. Others? All right, let's just do just a little bit of synthesis, and then we need to move on. I'll just show you a generic symmetrical ketone. And we'll do the alpha-halogenation reaction with Br2 and acetic acid. We expect to install one bromo group on the alpha carbon. We've made a stereocenter there. Naturally, we would get both configurations. That reflects the fact that the enol intermediate is flat and can attack the Br from its top or its bottom face. Now let's talk about what you can do with the resulting alpha bromo ketone. The basic chemistry that we're going to do here is going to be dominated by the fact that the bromo group is a leaving group. So go ahead and suggest some things we can do with the alpha halo ketone. Yes, Miriam.
Do elimination or to get a alpha beta ketone?
Sure, elimination. So E2 style elimination, that would give you and the proton that could be removed is there on the beta carbon. So the E2 style elimination would give you this, which is an example of an enone or an alpha beta unsaturated carbonyl compound, which you can then use for other things, right? The reagents that are of choice here, if you're thinking this is a 351 based reaction, you would have probably thought, can I use tert butoxide? There is one from your text, and it's oddly specific. Your text uses it without justification or sanctification or any explanation whatsoever. So the reagent is a combination of lithium carbonate, lithium carbonate as a base. Carbonate, if you're interested, and you don't have to be, you don't need to memorize this. Carbonate is the following ion, and it's a decent base. We've never really used it before for that purpose in 351, and presumably your text just ignores the potential for a competing SN2. So even though this base is not on your list of non-nucleophilic bases that only do elimination, when you see it in your text, that's what they're doing. I don't expect you to memorize it. If you see it on an exam problem, you need to recognize it enough to know what it's doing. If when you're solving problems you propose to use tert butoxide to do the elimination reaction, that's totally fine. I don't really actually know why they're choosing this base to do that elimination reaction. Okay, yeah?
Just curious, with talking about there, would we be able to just keep sticking more bromine on?
Could we add more bromines like on the other alpha carbon? That's a good question, and I think so, though there's not examples of that in your text, so I don't know whether it just doesn't work well or if it's uncontrolled or what. That's a good question. Others? No. Okay. How about the substitution reaction? So you could do an SN2 reaction with some kind of nucleophile. And hopefully this gives you some ideas about how to approach synthesis problems. If you see a molecule like this and you're like, how do I synthesize that? If you see what could have potentially been a nucleophile here, and it's bonded to the alpha carbon of a ketone, you need to be thinking, oh, I could have made that starting from the ketone with an intermediate that's brominated on the alpha carbon. Similarly, and let's just as just a brief review of chemistry you know so far, you should know by now a few things you can do with alpha beta unsaturated carbonyl compounds. So what have you got? Somebody was saying cuprate, so where does the cuprate add? 1,4 addition, yep, at the beta carbon. So if you see an R group that's beta to a carbonyl, you should be thinking, I could have made that from the enone starting material, which I could have got from the ketone by the alpha-halogenation chemistry. Let's see, I heard somebody else say, what if I used a Grignard or organolithium? Okay, that's going to do 1,2 addition, so you'd get that product. Somebody was saying, what if I did, and this is a 351 reaction, hydrogen and palladium on carbon? It turns out that carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds, so you can actually hydrogenate the double bond in the presence of the ketone and reduce the double bond. Why you would do that, since that takes you all the way back to starting material, is beyond me. And then let's see, we also have, if you wanted to reduce the ketone, you could use sodium borohydride or say lithium aluminum hydride, which I'm abbreviating as La, and that would give you the secondary alcohol. Okay. Excuse me. People used to tell me my head was going to explode. It's not happened yet if I hold in the sneeze, but I'll keep trying to do it, so if it does happen, you'll at least have an interesting show. That got grisly. Okay. You guys in the front are in the splash zone. If I let the sneeze out, you're also in the splash zone, so what am I supposed to do? Okay, excuse me. Well, that's it for chapter 17. Do enough practice problems on that alpha-halogenation stuff that you're okay with it, and you can do syntheses with it as well. All right. Chapter 18 involves some of the hardest stuff that you will do in organic chemistry. Yay! So you picked a great day to come. This is a chapter where we talk about what I'm going to call carbonyl condensation reactions. They're called condensation reactions because we're taking more than one carbonyl molecule and reacting it with another. And in a way, this is just an extension of what you learned in chapter 17. In chapter 17, enolates were the nucleophiles. And you get enolates from carbonyl compounds. In chapter 18, the enolates will be the nucleophiles, and the electrophiles that they attack will be carbonyl compounds. So we're going to combine what you did in chapter 17 with enolates with everything that came before in chapters 13 through 16, where we used carbonyl compounds as electrophiles. We bring both of those together. So to illustrate this, I want to introduce a reaction that is called the Aldol reaction. And it's called that because the product is a ketone with an alcohol in it. But to review what we've done so far, we're going to start with this innocent ketone, this acetone, and we'll note it's alpha carbon and it's carbonyl carbon, and let's just put it under basic aqueous conditions. Now, from what you already know from chapter, I think 14, you learned that under basic aqueous conditions, the ketone is in equilibrium with a hydrate. And you get that by attack of OH at the carbonyl carbon. All right, that should be not new to you. The hydrate reaction was boring because there's not that much you can do to prevent it from happening under aqueous basic conditions, and there's also not that much you can do with the hydrate. But it's something that happens. It's sort of this side equilibrium that's always in the background. We didn't actually say what the percentage was of hydrate formation. That will depend on a case-to-case basis. We've also said that the ketone here is in equilibrium with its enol form, which we've drawn like this. And in the enol form, the alpha carbon only has 2 protons, and the other proton is now on the carbonyl oxygen. So this is the enol. We've called the process of converting from enol to ketone tautomerization. And it happens under basic aqueous conditions via an enolate intermediate, which we've shown forming when the alcohol, or when the OH minus rather, deprotonates the carbonyl compound at the alpha carbon to give us this resonance stabilized enolate intermediate, which we've drawn a couple of different ways. Either way is okay. All of that should be familiar to you so far. And we said that at least given how acidic H2O is, which is to say not very, that there should be sort of greater than 99% under acidic, basic aqueous conditions, greater than 99% of our ketone should be in this not enolate form, and that there should be sort of that's the wrong sign, less than 0.01% enolate present at any given time. Okay, so we'll oops, we just about destroyed the recording by pulling out the plug, but we're still good. Try not to be clumsy. Hold my left hand behind my back so I don't bump into anything and disable the anyway. That's not going to fly. We're just not going to do that. Okay, so we're not saying a lot about, the relative amounts of hydrate and enol and ketone. The ketone form is more stable than the enol form. We are taking a stand on how much enolate is present, which is to say not much. Now, the one thing we've been ignoring so far is that your ketone starting material is an electrophile, and your enolate intermediate is a nucleophile. So now we're going to stop ignoring that, and we're going to show what happens when the enolate electrophile attacks the enolate nucleophile attacks the carbonyl electrophile. So here's your enolate. We'll draw it on the left. I'm going to draw it in the resonance structure where the negative charge is on the alpha carbon. A lot of people will prefer to draw it in the other resonance structure. It really doesn't matter. So here is your enolate nucleophile, and here is your carbonyl electrophile. Though this situation's unfamiliar, all you need to do is remember what you've learned about what nucleophiles do and remember what you've learned about what electrophiles do. When the carbonyl is the electrophile, the relevant orbital that we're going to dump electrons into is the LUMO, and we're thinking about the carbon-oxygen pi star. We're going to attack at, the electrophile will get attacked at the carbonyl carbon because that's where most of the LUMO is, and also because that's where all the partial positive charge is. So we'll draw an arrow from the nucleophilic alpha carbon of our enolate to the carbonyl carbon, and we'll get a tetrahedral intermediate. And the new bond that we make is between the alpha carbon of what used to be our enolate nucleophile and the former carbonyl carbon of our ketone electrophile. Only now the oxygen's going to have a negative formal charge on it, and then the two carbons from our ketone electrophile are here. Do you see how here this looks like a tetrahedral intermediate, right? Compared to what we've done before with carbonyl chemistry. Here's the carbonyl carbon, there's the oxygen, there are in light purple are the two groups that were on the ketone to begin with, and what's over here was our nucleophile. Okay? That's the new bond. Yes?
If the blue is the stereocenter, like your ketones,
Right.
symmetrical, is it a receiving mixture?
Yes, if we make a new stereocenter here at blue, which is to say if these two purple things were different, then yeah, you would get both stereochemical configurations. Because your starting materials are both not chiral, and so there can't be a preference for one versus the other. Okay, do I see another hand? Right, so the step we just talked about is reversible. And if you think about it backwards, what would the backwards step be? Well, electrons on the tetrahedral intermediate would kick down and kick off the enolate as a leaving group. That should not be too uncomfortable for you because we just talked about decarboxylation, where the thing that leaves or gets kicked off is an enolate, a resonance stabilized enolate intermediate. When we go in the forward direction, this is called an Aldol reaction. When we go in the reverse direction, this is creatively named the Retro-Aldol reaction, which doesn't mean it's dressed in clothing that you get off Depop, but rather, I guess that would be the vintage Aldol reaction. I have a 16-year-old that's crazy into acquiring clothing from Depop, by the way. He was kind of surprised when he bought these cargo shorts off Depop, and I'm like, I'm pretty sure I used to own those shorts and gave them away, and now you've purchased them from somebody else. So we ought to cut out the middleman. All right, anyway, so the retro-aldol reaction is where we kick off the enolate from this tetrahedral intermediate. I'm going to start calling what used to be the carbonyl carbon on our electrophile, I'm going to start calling it the beta carbon, because in our new molecule, it's beta to the carbonyl carbon. If instead of going in the retro direction, the negatively charged oxygen picks up a proton from water, that will get us to the first of two possible aldol products. I need just a little bit more space. So let me illustrate that here. Carbonyl carbon, alpha carbon, beta carbon. We call this a beta hydroxy ketone or carbonyl compound. I'll point out that this step is also reversible. Having made the beta hydroxy alcohol and deprotonated water to generate hydroxide, we could easily go back and have hydroxide deprotonate that beta hydroxy group. Okay? So that step is reversible as well. I don't want you to get the idea that I need to write out the word reversible in order for a step to be reversible, so I'm just not going to do that. Okay, so that is a legitimate aldol product. When you see a beta hydroxy carbonyl compound, you need to be thinking, I could have made that via the aldol reaction, and the bond that you make is the bond between the alpha and the beta carbons. And what was on the left side, or as we've drawn it here, the carbonyl carbon and the alpha carbon, that portion of the molecule is from your enolate, and the beta carbon, where the hydroxy group is, that portion of the molecule is from your carbonyl compound, where this used to be the carbonyl carbon and that used to be the carbonyl oxygen. So that's your first aldol product. Question so far? Yeah?
Is this all in under basic conditions?
Yes. Actually, it works under acidic conditions as well, though your text doesn't talk a lot about that, so we won't either. But you could draw a similar mechanism using an enol as a nucleophile under acidic conditions. What else? Okay, let's show you something else that can happen. So notice that the alpha proton, the alpha carbon, still has one proton on it, and it is possible for hydroxide to remove that alpha proton to generate a new enolate. Now don't worry, I'm not saying, oh, we're going to go on to do another aldol reaction. Instead, we get to this resonance stabilized enolate intermediate. I'm showing the negative charge on that alpha carbon. And what can happen, notice that that negatively charged oxygen is adjacent to the OH group. Negatively charged alpha carbon, rather, is adjacent to the OH group. Now, normally, we would think about OH minus as a terrible leaving group, but at least as compared to a negatively charged carbon as a kicker-offer, OH is an okay leaving group relative to a negatively charged alpha carbon kicker-offer. So what we're going to do now is basically an elimination reaction in which the electrons on the enolate kick down and OH leaves, and that will give you the following product where now there is a double bond between alpha and beta carbons. This is the so-called alpha-beta unsaturated carbonyl compound. This is reversible as well because the leaving group that leaves can come back in and do conjugate addition on the beta carbon to get you right back to that enolate. You would show that in arrows by having electrons kick down and attack the beta carbon and then move here onto the alpha carbon. That's the reverse backward step. Okay, so in the forward direction, this is an elimination reaction. And in the reverse direction, going backward, it's simply conjugate addition. So that's the aldol reaction. The alpha-beta unsaturated carbonyl compound is a legitimate aldol product. The challenge, of course, is that sometimes your text will show you one or the other, so you must anticipate both. Both products are in equilibrium with each other, so which one you get will honestly depend on which one is more stable. So I'm going to write down here, this is also an aldol product. And you won't really know without a lot of experience which one is more stable. I'm never going to give you a multiple choice question where I put before you the beta hydroxycarbonyl compound and the alpha beta unsaturated carbonyl compound and say which is the aldol product. Select the one that is right. And then you get angry, you debate about it for a while. What in the world was he thinking? Then you flip a coin, and then if you get it wrong, you come talk to me in my office and tell me what a jerk I am. And then I give you the points back. That's how the scenario would go, but I promise not to do that, okay? Either of these are legitimate aldol products. Sometimes you will need one in a synthesis, sometimes you will need the other, and you are free to use them. You're free to use the aldol reaction however required to get either the alpha beta unsaturated carbonyl compound or the beta hydroxy ketone. I will say that sometimes if there's some stuff out here beyond the beta carbon with double bonds, sometimes this elimination step gives you conjugation, and that can be stabilizing. One thing I want to point out about these last two steps. I guess I could number them. 1, 2, 3, and 4. Notice that the steps overall, 3 plus 4, are called sometimes a dehydration reaction, because look what you're losing. You lose this hydrogen, and then you lose the OH, so you're losing water. So you'll hear people talk about dehydration of the beta hydroxy ketone to give the alpha beta unsaturated carbonyl compound. Also notice what isn't happening in steps 3 and 4. We did not show the base removing the proton and then electrons kicking down and the leaving group leaves all in one step. That would have been an E2 mechanism, where a base removes a proton adjacent to the leaving group, a new pi bond forms, and the leaving group leaves all in the same step. Instead, we're doing something different. We deprotonate first, and generally we observe that that's fast, and then we eliminate second, and generally that's slow. And we call that, this isn't really important to anybody other than OChem nerds, but I will probably use the term in the future. We call this an E1CB reaction. People study these reactions, and if you study the mechanism of this elimination reaction, it turns out it's unimolecular in the concentration of beta hydroxy carbonyl compound, meaning how much base you add doesn't matter. It doesn't accelerate the reaction. So it's an E1 reaction. The amount of base you add doesn't matter, because the slow step is the leaving group leaves. We call this E1 because only the concentration of beta hydroxy carbonyl compound matters. The CB comes from the term conjugate base, meaning you use the base really quickly to make the conjugate base of your beta hydroxy carbonyl compound, and then in a slow step, that OH group eliminates. That's called an E1CV mechanism. Okay, questions so far? Yeah.
So with the beta hydroxy box, can the OH attack the other OH, the hydrogen on the other O, so that it can go to reverse direction?
Yes, at this stage, though I didn't draw it, the OH can remove this proton and that would take you back. Yep. Good. Others? Yes.
If all 4 steps are reversible, how often do we actually form an alpha beta unsaturated? And if we can, is that just because this reaction is a lot cheaper to form that, or why would we do this reaction?
Well, so first of all, yeah, the question is, why would we do this versus this? The answer is, nature doesn't care what you want. It's just a matter of which one is more stable. And that will depend on context. But as I said, if this double bond here between alpha and beta carbons happens to connect the ketone to another set of double bonds out here to establish a lot of conjugation, that can be quite stabilizing. I'm sorry, Matt, did you have your hand up and I missed it?
Yeah, I was just gonna ask, does E1CB always enolate? Is that always what's happening there?
Sorry, does E1CB always what?
Does it always involve having an enolate?
E1CB doesn't always involve an enolate, but that's one of the reasons why it happens here, because the enolate is resonance stabilized. Yep. Good. And yes?
Yeah, so if we have barely any of our enolate at all to start with, like 0.01%, and then
Yep.
every step that happens after this is reversible, if not just kind of slow, like how practical of a reaction is this to get what we're looking
How practical of a reaction is it? You'll do it in the 353 lab, and it works great. So the reason it works great is it's fast, and Le Chatelier's principle allows you to generate more enolate as soon as you need it. So enolate reaction is consumed, then you generate more enolate. Yep. Okay, the other reason you know this reaction works is, this is fantastic, because actually the retro-Aldol reaction is important in metabolism. One of the early steps of glycolysis is to break a 6-carbon sugar into 2 3-carbon pieces. We will do that very soon, and you will see that it involves a step where we start with a beta hydroxy ketone and we go backwards to the enolate and ketone starting materials. So speed of the reaction, forward, reverse reactions are both very fast. As to where the equilibrium constant lies, that's going to depend on the stability of the products versus the starting materials. For our purposes, most of the time in the text, it's going to be obvious. You're going to be given a ketone starting material and a base, and you predict the products, and it's going to be an aldol product, and either one of these is a satisfactory answer. Okay, others? Did I miss? I see. There you go. Thank you. Sorry.
Just to confirm, so we can't do this reaction with anything but a ketone as well?
Can you do this reaction with anything but a ketone as electrophile? Yes, you can. Aldehydes are fine. We will see that you can do this with esters as well, though it's a little more complicated because the presence of the OR group on the ester introduces the potential for a leaving group. So we're going to cover that as a separate reaction. But yeah, aldehydes and ketones, just fine. Others? Yeah. Is this competing with what? Hydrate formation? Yes. And again, because the hydrate doesn't really go anywhere, whatever you've got over here in hydrate will get siphoned back to the ketone and to the aldol product.
So eventually all the hydrate will...
Yeah, eventually all the hydrate would be consumed. All right, we're going to make this so much worse before it gets better. Are you ready? Let's do a little bit of retro thinking. Okay, this is an aldol product. And I'm going to ask you, what was the starting material? And I realize that I've combined a brand new reaction with something you hate, which is, dun, 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 a ring. When you see that, you automatically get OCHEM anxiety. This is exposure therapy to exposure aversion therapy to organic chemistry rings. Just ignore that for now and focus on the familiar. Okay? Let's identify the carbonyl carbon, the alpha carbon, and the beta carbon. Okay? Now, if we go back to what we just talked about, let's see if we can get oriented. And actually, let's think through this just one step at a time. Thinking backwards through the aldol mechanism. What is the immediate, and I'm going to use a retrosynthetic arrow to do this. What is the immediate precursor to this alpha-beta unsaturated carbonyl compound? What was the molecule that immediately preceded it? Do you remember? What was on the beta carbon? We had the hydroxy group, and what was on the alpha carbon? Negative charge, right? Okay, what was the immediate precursor to that? That's just its, the first aldol product, just the conjugate acid where a proton was there, right? Right, that's the first aldol product. That's the beta hydroxy carbonyl compound. Okay, now, did you remember what we talked about with the beta hydroxy carbonyl compound? I'm sorry, I just erased a bunch of stuff there. Here's the alpha carbon, here's the beta carbon. And you may need to scroll back or scroll up in your notes or turn the page. Which portion of the beta hydroxy carbonyl compound used to be the electrophile? Which carbon used to be the electrophile? Beta carbon. So that used to be the carbonyl carbon of our electrophile. Which atom used to be the carbonyl oxygen of your electrophile? was the OH, right? Which used to be the enolate. Where did the negative charge on the enolate used to be? On the alpha carbon. Good. And which bond did we make in making that first aldol product? The bond between alpha and beta, right? So, thinking immediately backwards to the precursor there, this is how you deal with rings. You think through it carefully and systematically, and you draw things as close as possible to the way they look over there. Here's the carbonyl compound that is going to become the beta carbon. Here is the oxygen that's going to become the OH group. Here is the alpha carbon of the enolate, and it's going to have a negative charge there, right? And what's the immediate precursor to that one? Yeah, it's the conjugate acid where we haven't even made the enolate yet. Okay? When you think through it, if you've mastered the mechanism and can think through it stepwise, you can get there. This is our starting material. Although, if you like, which you don't, we can draw it in an even worse way. 1, 2, 3, 4, 5, 6, 7. A 7-carbon diketone. Now, I'm pretty sure that when you looked at this starting material, when you looked at this product, this aldol product, the correct starting material was not in your mind. Nevertheless, on an exam, I can show you this and say which of the following is the starting material to make that from the aldol reaction, and you better pick this, right? So if that's not obvious to you, you need to work at it until you get it. Now, we've gone through this step by step backwards, but you can use a similar, and the real key came when we were at this beta hydroxycarbonyl compound intermediate, where we had previously worked through, okay, which carbon used to be the enolate, which carbon used to be the electrophile. You can do the same with the alpha-beta unsaturated carbonyl compound. The pi bond and the sigma bond between alpha and beta carbons were made in the aldol reaction. This side used to be the enolate, and that side used to be the carbonyl carbon. Where's the carbonyl oxygen? It's not there anymore. We lost it in that E1CV dehydration reaction. Okay. Now, I told you it would get worse, and it's still going to get worse. Yay, you're so encouraged. And the reason for that is if you were thinking about using this 7-carbon ketone as a starting material, and you were like, do an aldol reaction to get a product, what question are you going to ask me? Which product? What other products are you thinking about? You were noticing that I have 2 different alpha protons here. Now, thankfully, the ketones are identical by symmetry, so we don't need to worry about which ketone is the enolate and which ketone is the electrophile. More on that gem of a problem in a little bit. But here we do need to worry about which alpha proton is going to be removed. And some of you are sorely tempted to apply what you learn in chapter 17 about thermodynamic versus kinetic enolates. But I have a message for you. Enolate stability only matters for reactions. Enolate stability only matters if the reactions you do with the enolates are not reversible. The alkylation enolate formation was reversible when we were thinking about most stable enolates, but the alkylation reaction was not. However, I have shown you an aldol reaction that's fully reversible all the way back to starting materials where there is no enolate. And in that case, what matters most is the stability of the product. So your job is to take this starting material, and I want you to consider the product we'll call the orange product, that you would get from removing the proton from the less substituted carbon. And then I want you to draw the purple product, the one you would get from removing the proton from the more substituted carbon, and I want you to follow it all the way through, and then tell me which is the major product and why. Hint, it will have to do with ring stability. Okay, do that while you are listening to General Conference. I'm sure that's an approved use of conference time. So I will see you on Monday.